So hello everybody, thanks for attending this webinar on Kokkos. So we'll talk about CPU computing and a bit also of GPU computing. So as always, if you want to register to the school in the summer, you can also register right now. We still have some places, not much, but some in Annecy if you want to attend in Annecy directly. Otherwise, you can attend the school with satellite site or online with YouTube if you want. And we have few extra satellite sites since yesterday, so normally you can also do not hesitate to register, and hopefully you will get a satellite site near to your home if you cannot attend to Annecy. To explain everything to you, we have a trailer.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Gray Scott School 2026, a free, advanced summer school on high-performance computing. Designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge, simulating the Gray-Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kokkos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Gray Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Gray Scott School 2026, Europe's leading HPC summer school.
And if you have other questions, please contact Karim, Marie, or me. If you want to attend the school, if you want to create a satellite site, if you want to have all the information to get all the lecture and to be able to test all the containers and stuff like this. And without further ado, I will try to present our speaker today. So here we have Thomas from CEA. So a newcomer in the team. So we'll talk about wizardry with C++ today. So more particularly on Kokkos. So Thomas did his PhD on Mach regime. So once you do some fluid dynamic simulation, you know you have the sound velocity and you have several regimes on that. So you study that in your PhD. So you started to use Kokkos in the very beginning of your PhD. So you have a lot of experience on Kokkos, and you can maybe talk about that, the evolution on Kokkos on the time. It could be also interesting. Then you became a research engineer at CEA, so you work on Gisela simulation. So it was basically MHD, so magnetohydrodynamic simulation, so plasma physics and also some nuclear fusion simulation. And more generally, you are involved in on the GPU porting on the CEA applications, so a lot of application, in fact, to prepare the new exaflop computer use of Alice Ricock, the new supercomputer that we will have at CEA. And you use a lot of C++, so we will speak about a lot of C++ and maybe some different flavors of C++, because of course, you know, there are a lot of flavors on C++. And recently, you are also involved in deployment on supercomputer, because it's a really, really tough point. Also, of course, if you have the best application in the world, but you cannot deploy it on a supercomputer, it's a pity. So you have to be sure that everything is nicely done before, to be sure that everything will be efficient. And we'll have also the occasion to talk about that. So without further ado, let's start the presentation. So if you have some question, you can use the chat. We will answer all the questions at the end of the session. And wish you a happy webinar. Thomas, it's up to you.
Yes, thank you, Pierre, for the presentation. Thank you for the invitation. I entitled my presentation An Introduction to Kokkos on CPU, but also on GPU. This is also a joint work with the rest of my colleagues from the Sycl team that I will briefly mention later. So why are we talking about Kokkos today? The reason are that we are facing a few challenges in HPC with the arrival of exascale computers that lead to an hardware diversity. On the right-hand side, you can see a table of the top 500. So if you don't know about this this ranking, it's a ranking of the, as it suggests, the 500 most powerful computers in the world, that is updated every 6 months at ISC and supercomputing. And here I put the top 5 super computers. You can see, so El Capitan, Frontier, Aurora, Jupiter, and Eagle. These are, so the first 3 computers come from the US. Jupiter is installed in Germany, and Eagle is again in the US. They are built from different vendors. And what is more important to us today is that the main architecture that gives the main computation power of the computer comes from here on GPUs. The first one, the El Capitan computer, is equipped with AMD MI300A architecture, which is what we call an APU. It's a more integrated CPU and GPU architecture. The second one is MI250X, which is a discrete GPU. So it is really decoupled from the CPU. The third one from Intel is the Intel GPU Max, and it's actually the only one, the only GPU from Intel for HPC. And the fourth and fifth positions use NVIDIA GPUs with Grace Hopper for Jupiter. So again, this is an architecture that is a bit more integrated with the CPU, which is the Grace part of the Grace Hopper, and the Hopper is the GPU. And for the last position, it's a discrete GPU, the Hopper H100. So we can see that we have 3 different vendors for the GPUs. All of them use different GPUs. And as you may know, these vendors provide different native ways of using their own GPUs. For AMD, they do the promotion of the heap stack. Intel pushes to use Sycl, the standard Sycl. And as you may know, NVIDIA is developing the CUDA programming model. So If you want to be able to run on all these architectures, you may need to duplicate your algorithms unless you have a tool that allows you to write a single time your algorithm and to run on all of them. Of course, there are also CPUs that I will not talk about much in this slide. And you may also want to target the CPUs of the computers, which don't need more than C++ to run on, but you also need a threading, for example, programming model to run on them. So the Kokkos library, it's a C++ library that aims to provide a performance portability layer, so to avoid the user to have to deal with the vendor APIs, so that it writes single time the algorithms and can run on the different architectures. And so Kokkos hides the multiple backends that I just mentioned. So in more detail, Kokkos is a library that aims to provide a shared memory programming model and provides answers to data parallelism. It heavily uses template metaprogramming and function objects to target the different backends, underlying backends that you need to use to target the GPUs. It also tries to keep up to date, to be up to date with the more recent C++ standard. So as of the last version of Kokkos, Kokkos 5 or 5.1 more recently, we started to rely on C++20, which is, up to my knowledge, the most recent C++ we can use to target GPUs. It targets the major architectures we can find on HPC clusters. So regarding GPUs, you can run on AMD, NVIDIA, and Intel vendors, GPUs. And you can run on multi-core CPUs, either with OpenMP or with the threading, the C++ threading library. We also explore cutting-edge architectures that are more exotic, like the Next Silicon data flow accelerators. I say we because CEA recently joined the effort of contributing to Kokkos. So historically, Kokkos has been developed at Sandia National Laboratories, so it's a US national laboratory. At that time, at first it was integrated into the Trilinos project. It was then extracted to be standalone. And then after the Oak Ridge National Laboratory also joined the effort to maintain Kokkos and to target AMD GPUs. And more recently, the CEA, so the Commissariat à l'énergie atomique et aux énergies alternatives, decided to invest in Kokkos to be able to port the CEA applications on GPUs for the arrival of Alice Lecoq, as Pierre mentioned. So it takes the form of the SEXA project. So we are a team of developers and we contribute to Kokkos for new features, for maintenance, for dissemination, and for also our own needs in the CEA applications. One important note is that Kokkos is now an HPSF project. So HPSF is a Linux foundation. It stands for High Performance Software Foundation. And it's important to us because it's a sign that it's not only a US project, US government project, but it's a multi-institution governance where we can make decisions to answer our needs. It has also a large and growing community. You can find us on the Slack. We have a Kokkos Slack and we are quite active and reactive on it. So about the Kokkos programming model. So as I earlier mentioned, the key idea is that the user writes only once its algorithm and is able to run anywhere. The key thing is that you control where you run at compilation with some compilation options where you select whether you want to enable a CUDA build or a heap build to select whether you want to run on NVIDIA or AMD GPUs, for example. It provides some abstractions. So here on the right side, you have a picture of an abstract node on exascale architecture, where you have on blue and on yellow the execution resources. So you have the cores of the CPU, and on yellow the different accelerators you can find on a node, and in green the different memories you can have on the node. The idea is that in Kokkos this translates to abstractions. So in Kokkos you have the notion of execution space, so that will let the user specify where the instructions will run. You have the notion of the concept of memory space. So this gives the control of the user of where the data should be allocated. An execution policy, so how the work should be scheduled, and an abstraction of the data. So in HPC and scientific computing, we usually need multidimensional representation of the data. So just or you can call it tensors. Multidimensional arrays to help manipulate the data. So in the presentation, I will use multiple times this example where we will gradually modify it to introduce Kokkos. So let me introduce it. So this is a really simple example where we have the main function in C++. And in this example, we want to initialize a two-dimensional array. So until recently, we didn't have multi-dimensional arrays in C++. So I just chose to do, in this example, to do a row allocation and a linearization by hand. So we have 2 dimensions. One is of size nvar, and the size is known at compile time. So you can think of it as 2 variables attached in a mesh of size nx. And we do an allocation of integers of size nx times nvar. We use a C loop, C-style loop, to loop over all the elements of the array. And we do a manual linearization using the integer ix and hard-coded 0 and 1 that represents the second dimension. And we initialize it to some value. It doesn't really matter. And then we deallocate and return. So this is the example I will use, and we will gradually update it. The first thing to know about Kokkos is that it will give you parallel patterns. So if you for example, Sycl, you will recognize some the way to program in Kokkos. So these are the core basic algorithms you will need to build more complex algorithms. So the first one that I will introduce is the way to parallelize basic loops. So in this algorithm, you pass a string that is used for debugging or for tuning and profiling. The second parameter is the number of iterations you want to make. And then you pass a function object. So the Kokkos lambda is a macro that you need to use if you want some portability for GPU. We can talk about it later if you want. But here, this is just, it hides the lambda expression with a copy, a capture by copy. You must pass a function object that takes a single integer in this signature. This function will be called n times. Each invocation will get a different ID that is represented by the integer that you get from the parallel for. One important thing is that you cannot rely on the order of execution. They can be called in any order if you want to have some portability. The second algorithm is a reduction. You need a specific algorithm for that because if you try to implement it with a parallel for, you will likely get a data race. So you need a specific algorithm. It's a similar signature. So here you call parallel reduce. Again, you pass a string that represents the name of the algorithm you are implementing. Again, an integer that represents the number of iterations you are making. You get an integer that represents the current iteration. And you get a second, you need to have the signature where you have the local sum. So here it's a summation. It's the local value to the thread. In the body of the functor you are implementing, you have a local contribution to this variable, local sum. and Kokkos will take care of updating the global value that is represented here by some result. And finally, we have another basic algorithm, which is a cumulative reduction called parallel scan. Again, you have the same signature, but here you have a third parameter in the function object, which is final, which tells you whether, so this algorithm is a bit particular because the function object you are passing can be called multiple times for the same ID I, so the same integer I. And this Boolean value, is final, indicates whether this is the final pass, and this is the at this time if you want to store the result. In more Python notations, this would be similar to NumPy console. One important thing also is that by default, the algorithms are dispatched asynchronously. So when the CPU encounters the call for parallel for, it dispatches the algorithm, but it doesn't wait for the results of the execution of the parallel for and continues to the next instruction. If you want the CPU to block on it, you have to fence. So there is this function in Kokkos to let the CPU block until the result is ready. Let's take the example I showed earlier and modify it. So I just removed the main part and kept only the loop, the initialization of the array. So here the C-style loop disappeared in favor of the call to parallel for, and I kept the same way to initialize the array. So I'm using Kokkos lambda, and the integer that was updated in the C-style loop is now coming from the lambda and generated by the parallel for function. So if you compile Kokkos on for CPU backend and OpenMP, let's say, here this time you have a parallelization of this algorithm just simply by modifying the C-style loop by parallel for. But of course, it doesn't still run on GPU. As I mentioned earlier, we have the notion of execution policies that tells you how the work is scheduled and how it will execute. So we have different policies for that. In this slide, I'm presenting the basic parallelism. So these are made for tightly nested loops. So we have a 1D chunked iteration with the range policy, and a tiled iteration when you go to higher dimensions. So the idea is that you replace the integer that we were passing. We were passing n directly to parallel for, and this time we pass an object, here an object of type range policy that you construct with some parameters. So the parameters represents the first item you want to, the first integer you want to generate, and the end of the range you want to iterate. You have an optimization parameter, the chunk size, which represents the size. So the range is divided into chunks, and this chunk is given to one thread. You don't have to specify it on the first implementation. This is really an optimization parameter. Similarly, the MD range policy, so that you would use here instead of the range policy, has ways to specify the way you want to, the order of iteration, whether you want the first or the last iteration to be the innermost. And these policies are good for caching on CPU and coalescing on GPUs for tightly nested loops. We have a more advanced policy, which is hierarchical parallelism, or team policy in terms of Kokkos. So hierarchical parallelism is more like Sycl terms. Because one thing to note is that you cannot nest the basic parallelism execution policies together. So going back to the previous slide, you could not call another parallel for here with a range policy or ND range policy. This violates the semantics of Kokkos. So if you need that because your algorithm is more complicated and has some hierarchical structure in terms of parallelism, the tool to use in Kokkos would be team policy. And so in this API, you pass an object of type team policy. You tell how many teams you need and of what size. And instead of getting an integer here as an ID of the for the functor, you get a handle over the team. And with this handle, you can request how many threads you have in it and what is your ID in the league of teams. And then with this handle, you can construct other execution policies that you can pass to more parallel for. And here we have a call that is similar to the previous range policy, but as the difference that here we pass the team handle and again the number of iterations we want to make within this team. So the work, so we have to do n iterations of this functor, and the work will be distributed among the threads of the team. So this makes on CPU group of threads, and this basically maps to CUDA blocks on NVIDIA GPUs. You can also, with this parallelism, this execution policy, do some scratch memory allocation, which can be which can give you access to some very fast memory space on the GPU, for example, with the shared memory of a CUDA block. Here we have a 1D iteration with this parallel for, because we have here you can see only one integer, but we have also multidimensional loops, parallel for loops in the hierarchical parallelism. The final concept that I want to introduce for the execution part is the notion of execution space that will define where you want to run on your node. So typically, Kokkos will define one execution space per backend it implements, but these types are only available when you correctly compile Kokkos. So if you compile for CUDA, you will get access to CUDA, and to heap if you compile for with the heap backend. So this is not portable if you directly use them. So you really want to use the aliases we provide. So default execution space and default host execution space, that depending on the way you compile Kokkos will change the value. So for example, if you compile for GPU, for NVIDIA GPUs, you will get for default execution space CUDA, and for default host execution space either Serial or OpenMP if you also enabled OpenMP at compile time. This instance of execution space can be passed in the constructor of the range policy or MD range policy. So this is another way to control whether you want to compute on the host or on the device by passing here default execution space or default host execution space. So let's try to use that on this example. So before we just introduced the parallel for instead of the C4 loop, and here we replace the integer by a range policy. We get the same iteration space. We have to provide the first iteration ID, so 0. Here we can see that we have two instructions that are independent. So one idea could be also to use a 2D range, and that's the idea of this other implementation. We create this time another execution policy, MD range policy, where we specify that we have a two-dimensional space to iterate over, and we give the beginning of the iteration space in each dimension, so 0 and 0 for both. But this time we specify nx that represents the first dimension, and 2 that represents the size of the second dimension. And so this removes one instruction in the function object. And here you can notice that instead of having only ix, we get also a second integer that represents, in this case, the ID for the variable we want to initialize. At this level, so we have more parallelism, but we cannot still run on the GPU because here we still have this allocation that is made on the host. On more recent GPUs, this could work, but this is not portable enough. So the idea is to use a container provided by Kokkos, which is called a view. So it's a multidimensional array with different template parameters. So parameters that you need to provide at compile time. Some of them are optional. Only the first one is mandatory. It represents the data type you want to allocate, whether you want to allocate integers or floating points. The second parameter gives you control over the layout. We will see that in a few slides. The third parameter is the memory space. So typically where you want to allocate your data, whether it is on the host or on the device. And the final one is the memory traits. It's the way you want access your data, whether you want an atomic access or whether you provide non-aliasing access. One important thing is that the copy semantics of the view is a shallow copy. So at the construction of a view object, this allocates data. And if A and B are two views and you assign B to A will just alias B and increment a shared reference. So it's really similar to NumPy arrays or the semantic of shared pointers in C++. If you really want to do a deep copy, so you have two different arrays, and you want a copy of the underlying values, you have to call Kokkos deep copy. Also, this class was at the origin of the design of the now standardized MD-span that was introduced in C++23. And more recently, we worked on making the implementation of Vue more aligned with MD-span. So as I mentioned, memory spaces, similar to execution spaces, help to locate where the data resides. So we have different memory spaces related to the different backends we have. But if you want to be portable, you also need to use some aliases. So there is the host space that is always available. And if you want to refer to the memory space of a device, the way to do it is to get it through the execution space. We have another memory space called shared space that implements the managed memory, for example, in CUDA. So these are automatic transfers between the CPU and GPUs, and that will avoid you to do some deep copies. But still, you need to be careful of synchronization between the host and the device with this memory space. And another memory space that I mentioned earlier with hierarchical parallelism is the scratch space, which exists only at the time of a kernel and does not survive after a kernel. So the memory layout, I mentioned that it is a template parameter of the view. When you deal with multidimensional arrays, actually the underlying memory is just 1D memory allocation. And the layout is there to do a mapping of the multidimensional, the multi-index you are passing to the array and translate it to an offset from the beginning of the 1D array you allocated. So we have different strongly typed memory layouts. We have the layout right, which indicates that the fastest the unit stride is on the rightmost integer, and on the layout left on the leftmost integer, and layout stride, which is more custom stride, where the values of strides are left to the user. And this is an important notion when you want also to optimize your application. You need to control the memory layout if you want to have a good cache access on CPU and good coalescent accesses on the GPU. So this is not needed at the first implementation of your algorithm in Kokkos, but this is an important notion when you are in an optimization phase. So let's do this update on the example. We replaced the call to new with the creation of an object of type Kokkos view, where here we indicate that we want to allocate integers, and we have two other parameters to pass that represents the fact that it is a two-dimensional array, where one dimension with the star the size is known only at runtime, but the second dimension is known at compile time. And this is the way in Kokkos to provide it. And we pass a string, again, similar to the parallel for. It's a way to keep track of the allocations when you do some profiling or debugging. And we pass only one size here because only the other one is already known at compile time. And when you want to write into the array, you use the function call operator of the class view, and you pass ix and iv. And the layout of the view will take care of the linearization we were handling by ourselves earlier. And at this point, the code is getting portable. You can run on CPU and GPU if you recompile Kokkos. This is valid GPU code. You may wonder how to get back the access on the CPU when you allocated the Kokkos view. There is a notion and concept of mirroring view in Kokkos. So that represents a view in a different memory space. So it has the same other properties like the shape and the layout, but with a different memory space. So this is a way to be able to get back your data or to push your data on the device. So we have the create mirror function that always allocates compatible view on the host or on the device, given a Kokkos view. And create mirror view that if you compiled only for CPU, you likely don't want to reallocate a second view on the host because there is only the host available. And the create mirror view takes advantage of the strongly typed view to not reallocate a new array and do a shallow copy of the given view. So if we look at the example, we have our parallel for that initializes array on the device if we compile for GPU. And we can use create mirror view. We pass an execution, a memory space. We pass the array that is located on the device. And we get back a Kokkos view, and we can copy array into the array host. And array host can be passed to a function that will do C-style loops on the host. It will be, you won't get invalid memory accesses with this array. So if we compare the final implementation compared to the original implementation, you just need to add to what I showed earlier, an initialization of Kokkos. So this is a scope guard. So that will take care of initializing and finalizing Kokkos. You have a different way of allocating your data. Instead of new, you have an object-oriented allocation, which represents a multidimensional array, and a parallel for that replaces the C-style loop, and that is able to run both on CPU and GPU, depending on how you compile Kokkos. So not much more complicated than the original implementation that were only sequential on the CPU. Another important point that I wanted to mention with the views is the concept of subview. You may know that in NumPy, you can slice your NumPy arrays with the colon operator. We have the same concept in Kokkos, where a subview is just another view with lower dimensionality. So you specify slice specification. You want to where you want to slice your data, whether you want to keep a dimension, whether you want to take only one point in a dimension or a range of points in a dimension. This can be done on the host or inside the parallel for. This is valid. And as I was saying, this is similar to other languages or libraries. And this span, I don't think it got to C++23, but I think it will be available in 26. So there is a sub-mdspan feature like we have subview in Kokkos. So if we apply this technique in our example, so we get back the two-dimensional array, and we can call Kokkos subview. We pass the original two-dimensional array as a first parameter, And here, in this case, we say that we want to keep all the range in the first dimension, but we only keep the value 0 in the second dimension. So we get back here a 1D view. When we want to get the data out of it, we only need to pass one integer, and we can just use 1D parallel for to initialize this. And we can do the same for the second value of the second dimension. Subview is useful when you want to design APIs at a fixed dimensionality. And when, for example, you manipulate a higher dimensionality array, you can slice it and call your function that implements that works at a fixed dimensionality. So, for example, we could make this a function and reuse it with the subview function. That would be all for the Kokkos core notions that I wanted to introduce in this presentation. But Kokkos core is actually more than that. It provides portable atomics. So these are tools that you want to use when you want to write from multiple threads into the same variable. We have a SIND wrapper that can help when you are on CPU typically, and the auto-vectorization of the compiler fails for some reason. You may want to take back control of the vectorization using this kind of wrapper, SIND wrapper. We have other containers that have different semantics, different features, offset view that will let you start your array with an offset. So instead of, I didn't mention it, but Kokkos views always start at 0. It's an implicit starting point. With offset view, you can start at a different offset. We have dual view that help you manage synchronization between host and device views. We have scatter view that is linked to atomics. It helps you to manage algorithm where current iteration will write at an unknown location, a random location in a given view. And so you may have data races, and scatter view will help you to manage that. We have other algorithms, so standard inspired algorithms, sorting and random generation algorithms. I talked about reducing algorithms. So I mentioned the summation, but we can definitely do more complex reductions. And some helpers from the standard. You cannot use many features from the standard if on the GPU if you want to be portable. So we have helpers like an implementation of Kokkos pair, Kokkos tuple, Kokkos print that is quite helpful actually to debug, and more than that. That was actually only Kokkos core that I mentioned, but there is an ecosystem built on top of Kokkos core. I will briefly talk about Kokkos scanners, Kokkos FFT, Kokkos COM, that brings more high-level features than the basic algorithms that I introduced. We have also tools that help debugging, profiling, tuning, and linting that are quite helpful when you are writing production codes. And as part of the Kokkos project, we also help on documenting. We do some tutorials and some dissemination as of today. And we do have some online support, for example, on the Slack. This is for the Kokkos ecosystem, and we can even think of higher level abstractions, higher level libraries that are built on top of Kokkos and that are more maybe application oriented, more specific tools. So I will not talk much about Kokkos FFT because you will have another webinar about it. So this brings, as you can guess, fast Fourier transform algorithms. Kokkos FFT does not bring a new implementation of the FFT. It actually relies on existing external libraries that are really well optimized by the vendors or by the maintainers of the libraries. So it's a wrapping effort and also an API effort to make it seamless to use when you already manipulate Kokkos views. So to show you rapidly how it looks like, one thing that I didn't mention in the features of Kokkos Core is that we also have the complex types that are device compatible. And that's what we use here in this example. We do complex to complex FFT. So we allocate 2D views of 2D arrays of complex data. We initialize them by using a random algorithm. And we call the fast Fourier transform 2D from Kokkos FFT by passing an execution space so that will indicate where to run the algorithm. and passing an input and output array. And that Kokkos FFT will take care of calling the correct vendor library to perform the FFT. A word about Kokkos kernels. Kokkos kernels will bring you HPC-related building blocks like BLAS, sparse matrix manipulation, or graph algorithms. Similar to Kokkos FFT, it will either rely on vendor libraries like cuBLAS or HeapBLAS, or re-implement some of them. And instead of implementing your own, for example, GEMV, matrix vector multiplication, Kokkos kernels already implements it for you, or relies on an existing library and will likely be more performant than what you could achieve by doing it by yourself with a Kokkos Parallel 4 or Kokkos Parallel Reduce. So it looks like this. We take two-dimensional view that represents a matrix, a math matrix, two 1D vectors. We initialize the matrix. We initialize the vectors x and y. And we just do a GEMV call from Kokkos BLAS, and you get back the results into Y. So this is really simple and convenient when you want to build more complex applications. And the final application library that I wanted to mention is Kokkos.com, that will bring you you parallelism. As I mentioned earlier, Kokkos brings you shared memory parallelism. But if you want to run on multiple GPUs, multiple CPUs, one way to achieve that is to use a distributed memory programming model. And Kokkos, so typically in HPC, we would use MPI. Kokkos.com will help you handle distributed memory parallelism to avoid some code duplication and to do what we all do, manual packing or unpacking, and handle whether if the MPI implementation is GPU aware or not. That can be a bit verbose to do, and it will avoid you to do some mistakes about it. It's a modern approach. The library wants to also keep in line with sender receivers of C++23, I guess. And it doesn't only rely on MPI. There are also Nickel implementation that is pushed in the AI community to do some device-to-device communications. So if we take back the GEMV example, but here in this setup, it's distributed GEMV. In Kokkos.com, you would, similar to the default, the execution spaces we manipulate in Kokkos Core, you have a handle that takes an Kokkos execution space and a handle that represents a communicator in the case of MPI. So the idea is to do a matrix vector multiplication, a distributed matrix vector multiplication. So the data is distributed. So in this example, the first dimension is distributed and the second dimension is replicated. X is replicated and Y is distributed. So as you can see on the drawing on the right-hand side. So in this example, we initialize the X vector only on the part that concerns the process, and we do it by using the ID of the process, so given by rank, similar to MPI, with fence, if you remember, that allows us to know that the parallel 4 has been executed. And we engage a communication with Kokkos.com all gather, where we pass sorry, there is a typo here, it should be handle. And we do all gather in place. So the input and output are the same objects, X. So at this point, X has been only filled by the local data. And when we reach the wait request, the X vector has been filled by the data of other processes. So the green part has been given by the process 1 to process 0. And then when we have X that has been filled after the communication, we can do a local GEMV that will give the result locally for Y. If you are interested in Kokkos, we have a lot of resources. We have the Kokkos, we have some publications. We have a comprehensive guide and documentation online. You can find more. The repository is on GitHub. We have a cheat sheet that will help you remember the major API you need to use. We have tutorials that may be a bit old now on YouTube, but we have a more recent tutorial that has been done also by the Sycl team. I will conclude that Kokkos, I hope I could convince you that rather simple when you know a bit of C++. It enables performance portability by just recompiling Kokkos and your application. And at first, you don't need to think of the underlying hardware at the first implementation, just at the optimization stage. It's quite easy to adopt when you already have a modern C++ code base. And this is quite active project. We adopted it at CEA, and we are quite happy with it for now. And I will thank you and answer your questions if you have any.
Okay, thank you, Thomas, for the nice presentation. I have a lot of questions, but we will start with the question in the chat. So, question from Dimitri. Hello, is there a way to use Kokkos in your legacy code in Fortran, so Fortran 90 or 95? So is an alternative? Maybe OpenMP offloading?
There is a binding to help you construct multidimensional arrays between Fortran and C++, but it's not a pragma approach. So Kokkos will not help you parallelize your Fortran implementation. You will likely need to re-implement your algorithm in C++, but the binding can help you gradually re-implement your Fortran application, I would say.
Okay. We are talking about wizardry in C++, so porting that into Fortran is quite not so easy. Okay, so there is...
okay, maybe something else is that I mentioned we have different backends, and we have also an OpenACC backend, if I remember correctly. And so if you started already porting your application with OpenACC, it can be coherent to also compile Kokkos with OpenACC in OpenACC mode if you want to. Essentially, I would say it's simpler for your tool chain, because then you also need to play with compilers to compile both your Fortran and Kokkos library, and mixing compilers can be difficult sometimes, and programming models. So yeah, Kokkos can help on that sense that we have an OpenACC backend. OpenMP target OpenMP has been removed in Kokkos 5, but there is still the OpenACC backend.
Okay, another question from Mark. Thank you very much for the presentation. How would you recommend beginning the migration of an existing CPU-based C++ code base to Kokkos? What would be the incremental milestones in that planning process?
I would start with the data structures. It depends also. I found that it is easier when the application already has some OpenMP parallelization. So shared memory parallelism already available in the application, because typically you would replace your pragmas with a parallel for, parallel reduce call. So that would be one step. Otherwise, you will need to think also in terms of shared memory parallelism before going to put some Kokkos calls in your application. Yeah, thinking about data structures. There is one nice thing with Kokkos View is that there is an interoperability feature. So by default, when you called this constructor, the view will will allocate some data for you. But if your application has already an allocation system, here you can just, instead of using this constructor, you can pass a pointer. It will likely be a CPU pointer, so it will not get you to GPU, but you will start manipulating Kokkos views in your parallel for. And then you can maybe, in the second step, turn off your allocation system or update it so that it can handle GPU allocation. And then you have Kokkos view and Kokkos parallel for incrementally in your application. You don't need to change at once all your application into Kokkos. You can also definitely do a by-part update using parallel for and locally in your functions.
And maybe also I'm not pretty sure that with const size variable it will be possible, but if you don't have this kind of stuff, maybe you can use type def just to say, okay, before I have the type def with std vectors, and now I want to move to Kokkos views, just see what's going on. And you don't have to pass through all your code doing some replace and breaking your stuff. So if it's possible, maybe with the enva in bracket, maybe it will be not that easy. But if you don't have this one, it should be possible.
An illustration of the feature, you don't need. It's kind of an optimization also. The fact to pass envar in the template parameters, you can definitely pass it. Use it with 2 stars. You will maybe lose a bit of information at compile time that the dimension is known at compile time, but it's okay.
Yeah, for a force porting, it's okay.
You
have something working, you move to something else working, and then you can optimize.
Yeah. One thing I can also mention, I didn't talk at all about how to compile Kokkos and how to integrate it in your project. But I know that it can be also difficult because compiling for GPU is not that easy in the toolchains. So Kokkos is a CMake project. I know that some projects are still based on make files. It can be a difficulty. It's really more powerful if you can use it in a CMake project. So if your project is based on CMake, the integration is way easier than based on make files.
Okay, question for Ahmed Kadi. Data structure CD vector not reliable on GPU. Depending on your compiler, if you use NVC++, you can, which you have automatic copy of the memory as I presented before. Inheritance also leads to issues. If you port to GPU, it's not a good idea. Use tables, use tensors, and everything will be okay.
Dynamic polymorphism on the GPU is really difficult. It's not impossible, but you will likely have problems to make it work. It's possible, but you will also degrade the performance because the GPUs are really for data parallelism, and if you have an indirect function call on the GPU, you will degrade the performance. So if you can avoid it and do the dynamic polymorphism as a more coarse grain level than in the compute intensive loops, it's way better.
Another question for Mark. Is it possible that the original CPU data structures will need to be revisited to transition to Kokkos and efficiently leverage GPU capabilities? Of course, yes.
Yeah, you cannot avoid it, and it's not specific to Kokkos.
Yeah, it's specific to GPU.
Yes.
But as we say already, if you do that for GPU, your CPU performance will increase also, generally. So it's a good point. Good thing to do.
Yeah, on GPU, you have to focus on coalescent accesses, so multiple threads, consecutive threads accessing consecutive data. Depending on how you implemented your data structures, if it's already there, it's okay. And it's not. If it is not there, you need to try to think about that if you want to get performance.
Okay, so there is no more question for now. I will switch to a more general question. I have a lot of technical question after, but we will see that after. But typically, once you say at the beginning, CEA joined Kokkos development to add some features, typically, what's the kind of feature that you were missing that you would like to add in?
That we implemented already?
Yeah,
we would like to implement.
You implemented already because it was missing for you.
So Kokkos FFT was CEA initiative.
Okay.
So the full project, full Kokkos FFT project started like this. Actually, it was also, you may have seen here, DDC. So I'm developing this library that is based on Kokkos and brings some more features to multidimensional arrays. It brings compile time dimensions of arrays. So it's more an associative array. And in the case of Gisela, we needed FFT, portable FFT. So we started to use Kokkos Kokkos FFT started in DDC, and we extracted it and improved it with its own standalone application. We are working on improving SIMD wrapper. we're working on improving also MD range. Some people were complaining about the performance of MD range, so we benchmarked it and improved the performance on GPU mainly. You can have some. So actually, the release briefing. So we do release briefing for each version, minor and major version. And if you are interested in that, in the performance improvement of MD range policy, it was in the latest, the last release briefing on Tuesday. It's available online.
Maybe another question. Yeah, you were talking about profiling. Once you use a parallel 4, you can name the call, so you can get back the once you want to debug.
Yeah.
Apparently you have a dedicated system to debug, but if can you use, for example, Nsight with NVTag if you are used to? Is it okay? Yeah.
So
you keep your habit if you use Nsight and you use Kokkos, and then you can use Nsight either, and it's okay.
Yeah, we have so it's a plugin system, Kokkos tools. So you don't link to it at compilation. You load it at runtime. So when you compile your application, normally your application, and you can specify by using an environment variable or on the command line the path to a plugin, and it will be loaded at runtime with DL open typically. And we have multiple plugins. One of them is actually kind of a bridge for NVIDIA tooling. We have simple timer plugin that will help you see the time spent in your parallel 4 and your allocations. It can. We have also a system of regions in Kokkos. So because sometimes the world is not Kokkos. There are other libraries that work on the device, and when you do a porting, you have an existing code base that is not implemented in Kokkos, but you can still annotate these parts using Kokkos regions, and you will see them in the tooling. And you will see, you can name the region, and you will see that this region has spent some time doing that.
Okay, we have a question from Al also, and I have a question related to this one. Do you have performance measures for using Kokkos versus manual optimization, depending on the kernel, of course?
Yeah, Kokkos provides templates of algorithms, because here, when you look at Kokkos Parallel 4, the missing part is the function call that is provided by the user. So you need this final piece in the puzzle to start doing a benchmark. So we do have some benchmarks, but we have some representative examples. So typically on benchmarks, you have, the Babel benchmark, you have copy, you have a triad, you have multiple kind of standardized kernels. And yes, we do have some, I don't have them right now, but we have a dedicated part on the GitHub repository where we do some performance testing. And that was actually the work of MD range update to get more in line with the state-of-the-art performance. So we are more in line now with Raja or manual CUDA, the overhead. So that was the main work, was to remove some overheads we used to have in MD range policy. So it's now more in line with a manual CUDA implementation of some kernels.
Another question related to that: if I am a PhD student and I profile my application in Kokkos and I see that there is a bottleneck for one particular kernel call, can I try to replace this call by a CUDA kernel, for example, to get, okay, I have the state-of-the-art here, I know this one is faster, I try to figure out what is the overhead, maybe there is a problem of data alignment, maybe there is a problem of copy or whatever, to guess. Is it possible?
Yes.
Just for a particular backend, not for all, of course, but for example, for CUDA or for HIP.
Yes, exactly. The abstraction brought by Kokkos is really the minimum, but it stays close to the underlying backend. And so we provide some macro definitions. So you could have if-def over Kokkos enable CUDA in your code. And in that case, if you have the CUDA, you are using the CUDA backend, you could bring your own CUDA kernel. What you will have to think about is whether you are manipulating CUDA data. So whether you want to manipulate the Kokkos view or not, if you found some interesting performance gain to not use the Kokkos view for some reason, you can retrieve the raw pointer from it and the extent and the strides of the view. So you can kind of unpack the view. You can also get, so the execution spaces, in the case of CUDA, typically represents a CUDA stream. So you can also get the CUDA stream because if you bring your own kernel, you will need to ensure that it's correctly scheduled relative to other Kokkos parallel for. It will, that you are executing your CUDA kernel before, after some parallel Kokkos parallel for, and so you can get the stream, the CUDA stream, out of the execution space. I think that's all you need. You have the if-def. You can get the data from the view, and you can get the stream from Kokkos.
Okay. Maybe a last question, and then we will move to the question of David. The same idea. So if I want, for example, to use several streams, so I can use it directly in Kokkos. I say to Kokkos, okay, this parallel for, I want to use this
Yes.
execution policy. I don't remember the name. The execution space.
Yeah.
This one.
Exactly.
So you can use as many as you want.
Yeah.
But you have to look at your GPU specification, because sometimes you cannot use more than the maximum of the GPU, but you can use several if you can. And okay.
Exactly. So related to the interoperability question, if you already have created a stream, if I remember correctly, you can construct a Kokkos execution space from an existing CUDA stream. And there is a function called partition space in Kokkos, where from a given execution space, you can spawn multiple execution spaces. And with these given execution spaces, you can pass them to different parallel for. Of course, it doesn't enforce the hardware to do it in parallel, but semantically, they are asynchronous with respective to each other, the different parallel for.
Okay. So let's move on to the question of David. So we'll do a lot of matrix multiplication. So thank you for the talk. I'm in field of FEA, so I don't know this one, but apparently there is a lot of matrix multiplication. I am interested in performing many independent, small, dense linear algebra operation. So typically 500,000 of independent 3x3 matrix product. So typically projection, normally, maybe you can use also Vulkan and shader for that. I have been trying to play with NVIDIA Cutlass, a GEM API, you have that, or with Kublas, but there was a significant overhead compared to using a simple CUDA kernel for small matrix vector like this. I'm quite new to GPU computing, so maybe I misshoot these CUDA libraries, but if not, and if the custom CUDA kernel was most efficient choice, that's it. So, okay. Does Kokkos provide with an alternative to having to write my own CUDA kernel to perform a large amount of independent small linear size version? So that was my question before. So the answer is yes. You have to work a bit, but the answer is yes. Normally. And maybe with Kokkos view, so is there an efficient way to chain those operations, fuse the lambdas? Oh, that was also one of my questions. Can you fuse the lambdas? Is there a way to do that, or maybe it's a bit early?
I'm not aware of that. I mean, so what would be the question? You have two parallel for. So the source code is written with two Kokkos parallel 4, and you would like a way to fuse them?
I will get that. Yeah.
No, I'm not aware of that.
Yeah, it's maybe a bit too much.
I think it's more compiler work, and Kokkos is more on the library side. I'm not aware of such a feature.
Yeah, but maybe if you cannot fuse lambdas in the C++ itself, the compiler can do nothing. So maybe it's...
Maybe you can rework your implementation. I mean...
you can fuse manually your kernel, in fact. Yeah.
Exactly, yeah.
Just to try. But here we are talking of really a lot of number of 3x3 matrix products. So maybe, I'm not sure if Cutlass can do that, but MKL can CUDA a lot of small matrix multiplication. So you have a scheduler that the same ID as TBB, for example, and you can say, okay, I want to perform a lot of really small matrix multiplication, and then the scheduler will figure out how to start the computing. Maybe it could be the same. I'm not sure in Kublas, but in Cutlass should be possible normally. With the very last one, Cutlass 4, I think, if I remember well. You should have a way to do that. But the syntax is not that easy. It's a template wizardry with a lot of parameters. So, but normally you should be able to do that. And maybe for Kokkos as well, if you have parallel 4 and you break down your 500,000 3x3 matrix product in maybe few streams, and then or teams maybe.
I think
once you use teams, it's not a stream under the hood, it's just a parallel classic parallelization.
For this, here you typically get a handle on GPU that represents threads within a CUDA block. So you can assign one thread to multiple matrix multiplication, matrix vector addition.
Okay.
Yeah, that's definitely possible. I know that Kokkos kernels also have some features that are device compatible. So, I think Kublas is mainly a CPU C API that dispatches kernels, but CUDA kernels, but the API is on the host, and Cutlass is more compatible on the device. Kokkos kernels have also similar features, and that is compatible also with this hierarchical parallelism. So I think you should be able to call a Kokkos kernel algorithm where you give the team a handle. So you have some resources that represent threads within a CUDA block, and you can assign them to one matrix multiplication.
Okay. Or maybe in that case, when we have a lot of matrix products and really small ones, you can maybe use just one lambda to perform one matrix multiplication with the particular index that you are supposed to use. And that's it. And you start 500,000 kernels, threads is nice on a GPU. So if you have a H100, H100, stuff like this, it's okay. So I'm pretty sure that you get your code in your CUDA kernel, you extract the I parameter, the index, and you put that in a lambda and Kokkos, and it's okay. Normally, it should be nice. Question from Julien: is there a way to use Kokkos with the FPGA? And David is happy.
We have could be hacky, but we have a Sycl backend. Intel used to support FPGA using Sycl, but that would be for Intel FPGAs, I guess. No, I don't think so. It's not reliable. It would be highly experimental.
Okay, so
you need a compiler, C++ compiler that can target FPGAs.
Yeah, so the whole ICC or maybe C++, I don't know if it's possible, but yeah. So mixing with one API, Julien said, so maybe it's possible.
But definitely not supported by Kokkos.
Okay. There is no more question in chat. So yeah, a small question. If you forget to call Kokkos fence at the end of your program, normally you should have a guard, as you mentioned. Once you initialize the context, everything with, I don't remember the name, of course, but the scope guard normally should be okay for you. You just have to think about calling this one. If you forget, as in your previous example, maybe it's like you use some CUDA and you forget to do the device synchronize at the end, and then the program ends, but the GPU is still working.
It also means that you are not reading the data from the last kernel. So you are not consuming the result of the last kernel on the host.
Yeah, it happens generally once if you want to do some performance comparison and you're interested only on the kernel, sometimes you forget to get back your data and then you have a biased result because of that.
Okay.
So it can happen sometimes, but maybe it's better to use a scope guard.
I guess, yeah, the scope guards, when doing the finalization, will fence. Not sure. Yeah, I would definitely, if you really care about fencing, explicitly fence.
Yeah, okay. And yeah, by the way, for the scope guards, you have arguments. What are typically the arguments you can pass to Kokkos for maybe for the parallel scope or stuff like this? Or
yeah, so all the command line arguments are prefixed by -- Kokkos. So you can print the configuration that can be useful. If you don't remember how you configured Kokkos, it will print you what backends are enabled, and we have a few of compile options, so it will remind you what has been selected. You can
so how
select
you compile it, stuff like this to be
some runtime also information, whether you have HMM support or things like that. I used to use the num threads like this also, if you want to reduce the number of threads instead of using all the available threads.
Okay, by default, it's the full CPU.
If you compile with OpenMP, I think it will rely on the OpenMP proc. OpenMP proc num threads.
Okay.
It's another way also of selecting the threads. You can select your device, and sometimes on the compute node, you are only interested in one device and you want to select it. That's a way of doing it in a more portable way, because otherwise you have also backend related options like CUDA visible devices. I don't know if we have equivalents for other backends.
Once you specify the device, it's only one, or you can specify several?
I think it's only once.
Okay, but if you want to compute on several GPU, how do you do that? You use two programs? You use
I usually use MPI.
Okay.
And
so you cannot use two queues and say, okay, this one is for this device, this one is for this device, maybe two threads to handle the two GPUs.
I think it's now available.
Okay.
I think so. It needs to be reworked a bit in the application. I mean, it does not come for free. When you launch a Parallel 4, it will not dispatch on multiple devices. Because I think you manually, explicitly need to say that this array lives on device 0 and this other array lives in device 1. You need to take care of manually the synchronization.
Oh yeah. Of course, yeah. If you cannot have a really big array, then you split the array into several views on
exactly.
several GPU. But if you have several stuff to compute at the same time, you have parallelism that you know it's possible. Normally, you should you can split in two big tables, and then one for one GPU, one for another.
It has to be checked, but I think it's possible.
Okay, it's nice.
And yes, I was mentioning the tools, Kokkos tools, and it's a way of selecting the tool, either with using a full pass or the name of the binary, but it has to be available it has to be found from LD library pass if you do not provide the full pass.
So typically the plugin that you mentioned before.
Yes.
Okay.
Yeah. That would be the command line options we can use for Kokkos.
Okay, so Julien is happy. So this is okay, this is okay, this is okay. Oh yeah, can you compile with NVC++, for example, with Kokkos to get the unified memory software by default? Or if you don't use C++23 because it will break on... Is it possible to change the compiler or not?
NVC++, I think so. Yeah, seems to be supported. I don't use it. I usually use NVCC. But
it depends if you want to create your kernel or if you... Because with NVC++, as I mentioned before, you can use directly STD transforms to call the GPU directly, and maybe if you have a code like this and you want to move a bit on Kokkos to tackle some AMD GPU, if you can mix them at some point, it could be nice to not rewrite your whole application at once.
Yeah, never experimented. I was trying, but seems to be possible. Yeah. I can mention also something. You may know Godbolt.
Yeah.
If you want to try some API using Kokkos, let's try the latest available. You can try on Godbolt. Should not break. So it's pure CPU, but let's try. Yep, seems to work.
Or maybe, yeah, a question related to that. If you use G++ or Clang++ or NVC++ on CPU, and you forget some point you call a STD transform, and the STD transform will call TBB. Can you have a collision with the parallelism of Kokkos? During a migration, this can happen. So
yeah, I would be careful of missing threading libraries.
Or maybe there is a way to use TBB directly in Kokkos and not OpenMP, because it's another default backend for the compilers for parallelization. In C++, since C++ 17 at least, but
I don't think this is possible. We have for threading on CPU, we only have standard threads from the C. But yeah, we have standard threads from the C++. So I guess it's compatible.
It's not exactly the same kind of threads. The thread of TBB are more aggressive than the classic STD threads.
No, so because under the hood, Kokkos uses really manually the stud threads and will not call stud for each with an integer.
Okay, so you have to be careful if you want to
I think
to
so,
move. Yeah. The same for the static allocation on NVC++, so you will have some problems. So here, if you have extra parallelism with another library, try to be sure that you use Kokkos everywhere to be sure that everything is scheduled well.
Yeah.
Yeah.
Yeah, for the host backends, we have OpenMP threads and HPX. We don't have TBB.
Okay. Maybe it will come at some point, or is it planned or not yet?
Don't think so. Do you think there would be a performance benefit compared to existing backends, or it would only be for interoperability?
At least for interoperability should be nice, because all the compilers are using TBB in parallel backend by default. Okay. So maybe if you can use it, it's smooth the transition.
But I mean, don't you have already the plan then if you use parallel standard algorithms and you already also have stud threads in your program?
Maybe you should have some problem also, yes.
Okay, never thought about that.
So yeah, could happen. Some GPU question also. So you mentioned that you can share data between CPU and GPU automatically with Kokkos, but can you handle the shared memory inside the GPU? to be as close
Yeah.
as the core as possible. Is it possible?
I was fast on that. It's you only get it through this execution policy, so the more complicated one.
Okay, but you can ask. You can say, okay, I want
You
to
can
use this
ask,
one.
yeah. You have to prepare somehow the kernel. You can request a size of allocation you want per thread or per team, and at which level. The level indicating if you want it to be close to the threads, but likely you have less storage available, or if you want a higher level but less performant memory accesses. So in the global memory typically.
Okay.
So this is the scratch memory feature in the execution policy.
Okay, and can you also get the tensor core memory if you want to perform some tensor core computation after that?
I'm not aware of that. There is a memory dedicated to
Because
tensor.
you have BLAS, you have GEM in Kokkos, not in Kokkos core, but in Kokkos in general. So I wonder, maybe you can use the tensor cores directly, which is really powerful. In fact, if you want to do some matrix multiplication or matrix vector multiplication.
I don't think this is available through the device functions. Maybe through the more from the C host API of cuBLAS that we may provide using Kokkos kernels. But I don't think we have a C++ device function that will help you target these tensors.
Okay, so
because I'm not sure this is it available directly from CUDA already, or you
yes,
need.
it's horrible to use, but yes, but you don't want to use it.
Okay, you don't have to write PTX, do you?
No, it's not PTX, but it's not easy to write. So generally, I prefer to use cuBLAS directly, or to use an abstraction over cuBLAS, so I can use also MKL or LAPACK if I want. But if you can call directly a Kokkos gem, and then everything under the hood is done, and you will use tensor cores directly, it's okay. It's really nice. For the layout, so layout right, it's row wise, and layout left, it's column wise.
I'm
just to summarize.
Always confused about that. So my way of thinking for layout left and right, it's layout left is unit stride on the left, and my layout right is unit stride on the right, with a relation between the strides of each dimension. So stride 1 here, here the stride is the size of the last dimension, and so on. You multiply by the extent of your previous dimension.
Right, we can say it's more C++
yes.
way, and left it's more Fortran way.
Yes. Yeah.
But yeah, the naming is quite difficult. Nobody is agreed on that. Once you change library, it's difficult too.
About the layout, we have more layouts to come also, because the layout right and left actually in Kokkos are not exactly the same as in the layouts provided by MDSpan. Layout right in Kokkos would more correspond to layout right padded in C++.
Okay, yeah, it was.
So it doesn't have to be contiguous in Kokkos.
Okay, but you can add a padding if you want?
Yes.
Okay, and you can change the value in your padding, or you have 0 by default, and you have to deal with that?
For padding, you have to request to Kokkos some padding. I'm not sure you have a full control over the value of the padding.
Normally, 0 is better because you don't want to divide, but at some point, if you have to divide, 0 will be a problem. Okay, so this one is okay. So this one is okay. Oh, maybe, yeah, on atomic. Just a question, because in NVIDIA, they presented ridiculous atomic at some point that you can have an atomic between a full rack. Maybe it's not that scale in Kokkos, but typically once you perform an atomic, it could be a full CPU, full GPU. You have it's okay.
I'm not an expert on atomics. I don't think you can in Kokkos control I don't know the name of that, the level of atomicity you want.
Because you have an atomic defined and you have to use it well. Okay.
I think it's at the level of the whole GPU. It's atomic on all threads of the GPU, but not more, not less. That show you have control over the threads that will have this atomicity property.
Oh yeah, maybe also related to this one. Just think about that right now. Can you also have synchronization with what they call clusters in CUDA, but maybe it will be a kind of a team in a GPU? Is it possible?
No, I don't think so. We don't have such a feature. I think it's kind of related to the fact that it wouldn't be much portable because I don't think
there is not the equivalent on AMD.
I'm not sure. I don't know. I never heard of that for AMD.
Okay. So in Kokkos, you really want each time to have a mirror of functionalities on all the vendors. And if one does something really nice, but the other don't, you are stuck and you cannot say, okay, let's implement this one for this particular vendor. For all people here, it will be really nice. For example, to have the cluster or to have graphs that you can also have in Sycl, for example. It was another of my question. Also, if you want to have a full graph of execution running on your GPU.
Regarding the features we can add in Kokkos, the device features like this, I think we want an equivalent either on all the backends or at least something that may mimic the feature on a device that would have a hardware accelerated feature, let's say.
Okay.
Regarding graphs, we do have a graph API in Kokkos, so that will let you, not an expert on that, but as far as I can understand, it helps you get rid of overheads when you launch multiple kernels, small kernels. We do have that. Actually, the semantic is quite nice because it helps you express dependencies between kernels that we may not express really well when we just use parallel for like this. So let's say we chain multiple parallel fors. Sometimes the dependency is not that clear. And I think with the graph API, you would have functions similar to Kokkos.com where you have wait on the previous kernels you just dispatched. I find that quite nice.
Okay, it's really nice, yeah. Okay, so you can do this kind of stuff. Yeah, it's really
interesting. I never experimented that so far. I think there was a presentation. So at Sycl, one Wednesday per month, we have what we call a tea time. So one presentation in the afternoon. You can join actually also. We invite you. And if you have something to present, we also invite you to contact us. So it's really related to Kokkos and to GPU programming overall. And I think someone presented something about the graph a few months ago. You can find that on the Sycl website. We record them and we have the presentation slides if you want to look.
Okay. Oh yeah, question. Of course, it's more a question for Joel, but you mentioned you can use complex numbers?
Yes.
And how do you store complex to ensure vectorization of computing stuff like this?
About what do you mean? How do you store?
Do you have a struct of real part and imaginary part, or do you store vectors of real and vectors of imaginary, as in Eve, for example, to ensure that vectorization is really fast?
Here, I think in this case, I think it's an array of structure. So it would be a two-dimensional array containing the structure complex. So and complex would be two doubles.
Okay, so you cannot vectorize the. Because Joel has
I guess
you
don't have a choice if you want to refactor that into a structure of array. You either have to introduce a new dimension in the view that represents the real and imaginary parts. I don't think we have an out-of-the-box tool to do that.
In fact, it's the case in F. That was a question. And the same also for your example with two parallel 4. You start one parallel 4 for the first element, the first column of your table, and a second parallel 4 on the second column. This one. Yeah. If you do that, it will work, but you will kill your performances because you don't access contiguous data. At least it's really small data, but at larger scale it could be a problem. So maybe you can say int star envar and say int envar star to say, okay, the first dimension is known because I have first row of one value, second row of one value, and split on the rows to have a better speed
up. So what you suggest
is inverting.
I would do is rather keep the ordering, because it may break the code elsewhere because we changed the representation, the meaning of the dimensions. So that relates also to the DDC library. So I would keep the ordering of the columns and the semantic of each fixed, and I would add and I would play with the missing template parameter here, the memory layout, and play with layout left or layout right. I guess here we want contiguity in the in array 1. So we have to ensure that when we slice, we keep the contiguity in the result, and so you can compute the layout you want here to make that happen. So I guess we want a layout left here, so that when you slice here, the result is still contiguous.
Okay. So I have 2 questions left, and then we can finish on time. So you mentioned that Kokkos relies on vendors library. How do you handle the API if the API is not really cooperative for what you want to express?
Do you have an example in mind?
I don't know, the 12 parameters that you pass in MKL when you want to multiply 2 matrices, or this kind of stuff.
I participated in the development of Kokkos FFT. Yeah, you have to read the different documentation of each library. Fortunately, heap is quite similar to CUDA, but you still have to be careful because sometimes you may have just one parameter that changes the meaning.
You have a transpose somewhere, and then you're stuck.
Fortunately, in terms of feature, maybe not really in the same function signature, but at least in the features we expose, they all aligned quite well. We were not stuck of having a feature that we wanted to express, but one backend would not have it. I don't think we encountered this in Kokkos FFT. I don't know well for Kokkos Blast because I'm not really involved in the development. We had some subtlety with Kokkos FFT where the input array was not only read-only, for some transformation, it was also a work buffer. And so if we wanted to have an API where the input array is read-only, so it's something that I did not mention. If you want to lock your array to be read-only, you don't put const here. You put the const in the angle brackets, similar to undispan.
Okay, yeah, it's your integer which is const.
Yeah. And we couldn't make it, I think, for this particular function in Kokkos FFT because one of the backend could not promise the input array would not be overwritten.
Okay.
So if we want to promise that to the user, we have to make a copy and with some overheads.
Yeah, of course, you have to do as better as you can. If the vendor is not cooperative, it's not your fault. And maybe related to this one, and then I will get to my final question. I will leave you alone to be able to have some lunch. If I am a vendor, what did I have to develop to make sure that you can have a nice backend? So I can launch some kernels. I want to deal with the allocation, memory transfer, maybe some graphs. Is there anything you need, or is it really try to have the small backend as possible to be sure that it's easier to maintain for vendors?
If it is likely to be an accelerator, you need a way, at first, C++ compiler. We need a compiler that is able to parse the C++ and generate whatever instruction set needed for the accelerator. And yeah, some typically C functions that do accelerator malloc, accelerator free, and we will handle the rest.
Okay. And
a way to dispatch onto the accelerator.
So typically at some point it could be possible to have a backend with Vulkan, for example?
But Vulkan...
you don't have the matrix product, but you have all the low-level parts.
The question would be, how do you generate... So the kernel you want to run on the GPU is here. The question is, how do you generate the compute shaders? I'm not really familiar with it. Is there a compiler that can generate the compute shader or the intermediate representation needed for Vulkan?
You have LLVM with MLIR.
Well, okay, that may be possible.
Then you can do some magic. So you dump the MLIR kernel, so that directly, and then on the fly you convert the MLIR with the GPU that you discover on the fly, and normally it's okay.
Then yeah, that may be possible. Then
it's black magic, but you can do it.
Yeah, I don't know how you link then after because I think in Vulkan you need to load the shader.
Yeah, you need to load and you need to adapt the internal representation to the binary. So you don't have an embedded compiler, but a kind of, in fact, just to do the last part.
Yeah, if we can find a kind, because otherwise it would be difficult. We need a way to link this shader and to tell Vulkan how to find it automatically, and then
okay.
I don't know if there is much work to do, but it seems possible.
Yeah, so at some point it could be possible. Okay, so maybe last question. You mentioned about Nickel at some point.
Yeah.
So is it possible to have a communication between kernels inside the lambdas that we pass to run on the GPU?
That would be like NVSHMEM.
Nickel and NVSHMEM, in fact, now Nickel is using the same paradigm as NVSHMEM, but it was not the case before. So now everything should be symmetric in terms of allocation. Before it was not the case, but they had an extra overhead about that. So now they're aligned on NVSHMEM. But yeah, it's not exactly the same. NVSHMEM is point-to-point communication. Nickel, you can do ring, you can do a lot of stuff, but it's not the same implementation. But they work together, of course.
But is Nickel already able to initiate a communication from a device?
Yeah, device to device, a lot of device, in fact. For full rack is possible. So
I think the API provided by Kokkos.com is for now, CPU only.
Okay. But it will come at some point?
No idea for that. If I guess yes, if it can be proven that it can be found that the performance is good using that feature. Yeah. Again, if only NVIDIA is providing this feature, that would be problematic for portability.
Yeah, you have to ask Adrien for AMD part. I have too much work to do just to follow NVIDIA, so I don't have time for the other, but yeah.
Yeah, we don't want to be locked only for NVIDIA for such a feature. Yeah.
Okay, thank you for all your answers. So thank you everyone for attending this webinar today. Next week, we will do some magic in C++20 with Eve. So Joël will present Eve as so how to deal with that. So in fact, the same as Kokkos, but here it will be really only for CPU computing. So typically how to vectorize complex numbers, stuff like this, or sine, cosine, stuff like this. So we'll see that next week. Don't forget to register if you want to attend to the school. So normally you should have some satellite site near to you, and then you can also attend to and see, even if there is not much place left right now. And have a good day and see you next week. Bye.
Thank you. Bye.